Raulin on stage. He is part of the CIDRE team who developed a tool for program and malware analysis. The talk is called GUI-Mimic. This is a cross-platform recorder and fuzzer of Graphical User Interface. So Vincent, the floor is yours.
Thank you. So yeah, I work at the CIDRE team. I'm a PhD student at Centrale Supélec and INRIA. And I'm presenting you this tool that we consider for a purpose and that we want to share. It is GUI-Mimic is a fuzzing tool that works by interacting with the mouse and keyboard. But first of all, I need to explain quickly why we needed that. So, in our study, we focus on malware analysis. This is a malware is just a file or some parts, some code inside of a file that will execute some malicious actions. So when it reaches a certain target infrastructure and execute on it, some of the actions, we will study those actions to tell whether or not it's a malware, and more precisely, more interestingly, what is the family, which means what are the kind of actions that it took. More particularly, in our approach, we want to do what is called dynamic analysis, which means we want to run those sample files we want to analyze in a controlled environment, for example, in a virtual machine. But we will monitor them as they run. And when we think they've executed their actions, we will retrieve some execution trace information, to whatever that means, resource performance measurements, system call traces, and we will perform analysis from these traces. More precisely, we want to have a machine learning approach, which will give us some requirements. First of all, we need to generate a lot of these execution traces to be able to train our models. Furthermore, we want to be able to do some behavioral analysis, which means for particular softwares, which means we need a lot of traces per software to understand their behavior. That's why we also need some various data to be sure that we will explore all the possible paths to have the largest code coverage of a given software. And finally, for our particular need and some of our models, we want to be able to fuzz some goodwares, benign software, to learn their typical behavior. So, in particular, on most cases, the software we want to fuzz will not be designed to interact through terminal. Instead, they will have a graphical user interface, and that is what we will interact with. The problem is that if we want to generate completely random events with the mouse and keyboard, this is very ineffective, as we could click, for example, on dead parts of the screen and, for example, lose focus on the software we want to try. So instead, what we need to do is to learn some rules for the software we're currently fuzzing, telling us what are the active parts of the interface. So to sum this up, our tool needs to interact through the graphical user interface, by taking control of the mouse and the keyboard, and generate all the necessary events through that. To learn to make coherent actions, we need to record ourselves using the software. And then we will be able to trim these sequences, this recording, create some rules, some logical rules, to make sure the way we're using the software, the way the fuzzer will use the software, is coherent with its interface. We also need it to be fast, because we should not have to spend days teaching the software how to use a given program. But on the other hand, we want some randomization features, as we need to fuzz it, so we should not only play what we recorded. The software needs to learn more from the recording, learn how to do more. And also, we want to be able to target specific parts of the application, which means, for example, if we think we have more to look for in a certain use case of a software, we need to be able to tell our tool to focus on this part. And finally, ideally, this tool will be cross-platform to make sure we are not limited in our studies and that as many experts can use it. So first of all, I'm going to explain to you how the recording of sequences work when you record yourself using a given software. I'm going to talk then about how we represent the actions we are recording. Then I'm going to talk about the scenarios, which are the way we set the rules to tell our tool how to use our target software. Then about the editing work you have to do, you can do to be more accurate in your fuzzing. Then I'm going to talk about the events that we use to simplify your work and how the software, the system will interpret them. And then about some transformations that are made to ease your work and to add some more fuzzing capabilities. So first of all, about the recording of sequences, it is very simple. With the software, you just have either to press a button or to press a short key. By default, both control keys, quite unusual, to start or stop recording. From that, you will get a sequence of events, which is all that the system sends us, all the events the system generated from the data collected from the mouse and keyboard. Each of these events has its own information, like the duration of the time to wait before the event executes. For keyboard events, the keys that are used. For mouse events, sometimes the coordinates, sometimes the button used when it's a click, and the scroll amount. So now I'm going to show you how the recording works. So here I'm just starting the software. So here in this case, I'm trying to fuzz Visual Studio Code. So what I'm going to do is first record myself starting the application. So for that, I just type in a name for the sequence to generate, and then I start the recording. So I'll choose to start it this way. And once the system is the Visual Studio Code is started, I just press both control keys to stop the recording. From that, we've retrieved the sequence of everything that happened. Now I'm just saving the file. And to have a better code coverage, you should record yourself doing this in multiple different ways. So here, I'm going to record myself again, starting it in another way. This is to ensure that some malware, for example, might trigger on different conditions. By starting the software in different conditions, in different ways, I may reach those different conditions. Now I'm going to show you what is the content of a given sequence. So here I've recorded a few sequences, and here I'm loading a long sequence of a complete use of the software. So this takes sometimes to load, but as you can see, many different events, mostly mouse moves, which are infinitesimal mouse movements. And this sequence holds everything that happened when we use the software. From that, you've seen that there were many different events and a lot of events that were quite the same. So we created two classes, two types of events. Let's say, for example, we want to model a simple mouse move, which means a simple mouse click, which means we want to move the mouse to a certain place on the screen, then press a button. This is, from the system, what we get is a very long sequence of mouse moves, like moving from 2 pixels, pixels back, almost pixel by pixel, then a mouse press, and a mouse release on the same button. So all of these little events are atomic events. We cannot split them. And this is concretely the information we gather from the system. On the other hand, we decided to modelize that with what we call a synthetic event. This is just a merged representation of all these atomic events. And when we want to play it, to make sure the system understands, we need to develop it back into a sequence of atomic events. This has two advantages. First of all, it's much easier for us to manipulate. And second, getting rid of some of the exact information of the mouse paths allows us to add some variability. So for example, if we look at the sequence we recorded earlier, we could synthesize it by grouping the key that we use to type and the mouse moves. So here I'm going to show you how to what the synthetic events look like. So here I'm just creating an empty sequence, and instead of making all the events one by one, I'm going to create just synthetic events that will represent complex sequences, but just in a few events. So here, for example, I add a mouse click, so it means going to click on some specific place on the screen with some times, and then multiple clicks. I can precise the duration and the coordinates, so even I can set random coordinates. And also set the mouse button to use. So this event is added to the sequence. I'm going also to add another event. So keyboard inputs means typing some text. So I have to type in the duration before starting to type. And then what I want to type. You could type, for example, a certain specific text, but this is not extremely useful for fuzzing, or except in some specific cases. On the other hand, you could also add some random words to appear like the goal is to make it look like a real user. So ideally, some random English words. I can also precise the typing speed. And now this sequence is ready to be played. Now that, let's suppose we made enough sequences, we've recorded enough data to play, we want to make scenarios, which are a set of rules to tell the system how to use the sequences. So for example, let's say I've made a recipe book for a given application. This means a lot of sequences of different use cases. Ideally, you would not record yourself using the entire software at once, as you would have. This would not be a good material to explain how to use the software. Instead, you record yourself using specific steps of the software. So for example, I have multiple starting sequence, ways to start the application, multiple creating a new file, sequences, and so on. So now to explain our tool how to use the sequences, we will make a scenario which is just a sequence of regular expressions, which will tell it how to choose in between the sequences to make a valid scenario. So for example, I'd say save.star means I want you to choose a sequence which names begins with save. And then, at the moment of playing the scenario, the system will choose one sequence per expression and play them in the exact same order. So here, for example, I will make one of these scenarios. So to do that, I just have to insert the expressions. So for example, the first thing to do, of course, is to start Visual Studio Code in any possible way possible. So I will name it start.star. It is the language of Python regular expressions. So .star means any character, any number of times. So I just have to add a few sequences, for example, a few expressions. As you do this, you will be able to see all the possible outcomes. For example, a valid use case for Visual Studio Code would be, well, first to start the application, then create a new file. Here in this particular case, as you can see, I've only made one sequence name new file, so I don't need to put the .star. Then code something, and at the end, exit. So on the software, on the tool, you will have many information. Here you could see all the possible choices that would come out of this scenario. You can have also all the outcomes, or only for a specific expression. And once this is done, I'm able to play the scenario. Now, just a bit, I'm going to talk a bit about the editing work you can do to improve your sequences. First of all, let's say you have recorded some things, but you want to add more sequences. The first thing you can do is just to add, as I've shown earlier, your own events, ideally synthetic events, because they are much, much easier to handle. And once this is done, you can apply transformations. Transformations can be applied instantly to ease your work. Let's say you want the whole sequence to last twice as long. You might not want to edit each event individually. To do that, instead, you can apply transformations to change all the events at once. Once this is done, at the moment of playback, two steps will be done. First of all the synthetic events that you use to easily manipulate and easily understand the sequences will have to be developed back into atomic events, as this is what the system expects. And once this is done, we can apply some other transformations that we will have scheduled. Ideally, those transformations are random transformations. The idea is that each time you will play them, the corresponding sequences, you will have a different outcome. So here, for example, I'm going to show you what a playback looks like. So here I'm playing the scenario that we made earlier. Here it's important to note that I'm not touching the keyboard and the mouse. So here, the scenario, if you remembered, contained the expression start, new file, which also include, I think, saving a file, and code and exit. So here it will choose one sequence corresponding to each case. So here it will, I think it will save something. Yeah, it will save the file, and then code something, and then exit. As for maybe you want to know about the complexity, this tool is quite lightweight. You won't have any complex operations. All the operations are on sequences of relatively small sizes. So we've made it so all the operations are at worst linear, both in space and time. So yeah, I'm finished typing. Here it tries to run the code. And once this is done, it should exit the application. And once this is done, you will collect the exact sequence of event that was played to be able to replay it if you want to repeat the experiment. Now I'm going to talk a bit about these synthetic events, as this is not, these are some opportunities. Developing them offers some opportunities. First of all, about the mouse click events, when you go to click on certain position on the mouse, they develop back into the way they were before, which means a sequence of mouse moves, infinitesimal moves, then a mouse press and mouse release as many times as needed, if you want to do a double click or more. But the path is not saved in the event, in the synthetic event, so we have to create it. And this is a good fuzzing opportunity. What we do is choose a random point on a discus centered in the middle of the starting point and the ending point, and make a Bezier curve from the a degree 2 Bezier curve from those 3 points, and this will be our mouse path. On the other hand, for keyboard inputs, we have to, you can type in any kind of text your keyboard can type. For that, we have to handle many corner cases. Uppercase cases are quite simple to handle, much harder for special character cases. And this will develop into a sequence of key presses and releases ordered in the right order to type the text you wanted it to type. Now I'm going to talk a bit more about the transforms. So the transformations are just functions that take on an event and returns 0 or more events. The idea is to apply this, you define this function, or you take an already made transform, and this will transform an entire sequence. So the transformation can be applied, as I said, at 2 times, either at editing to ease your work. So I took the example of lengthening the duration of your sequence. There are much more. You can also, so that was a time dilation. You can also filter some events. For example, let's say you don't want any keyboard press on a certain key. I don't know, because you don't have the key, for example. And on the other hand, you can also apply a sequence at random time. So the idea is that this is much more useful to do that for random transformations. For example, the time noise. It's very useful in the case of a keyboard input. When you develop a keyboard input event into a sequence of keyboard press and keyboard releases, the corresponding sequence will have, all the events will have the same duration, which is quite not human-like. So instead, you can schedule a time noise transform, which will add some noise on the timestamps to make them a bit random. And since this is applied at runtime, every time you play the sequence, you will have a different outcome. You can also, for example, randomize slightly the mouse moves to make sure you don't click at the same time, exactly at the same place. So here I'm going to show you how to make those transforms. So here I've opened, it's the sequence that we defined earlier. I'm going to, first of all, apply time dilation transformation. So the only thing I need is the dilation factor. But here, I don't really need it because we made a synthetic event sequence. That's very useful. On the other hand, applying a time noise is always useful, especially when there is keyboard input events, which there is here. And this is done. When we will play the sequence, this transformation will be applied and add some random noise at the execution. So to conclude, we made this tool to mimic the interactions with a given software of a normal user. It can generate most of these kind of interactions. Our representation in sequences and scenarios ensures that all the interaction it will generate are coherent with the interface of the software to make sure we don't lose control and we keep fuzzing the software as we want. It is quite fast. Here I only had to do less than 10 recordings, and I was able to run some fast, some simple fuzzing. The scenarios, the synthetic events and transformations are all made to offer you good fuzzing capabilities to make sure to increase the code coverage of the software you're testing above what you've recorded. The scenarios are what allows you to target specific parts. If you record sequences using specific part of the software, you just have to incorporate more scenarios using these sequences, or to make sure the scenario uses these sequences the most. And we've tested it on multiple environments, on multiple, for example, Linux distributions, and it works on those platforms. And you can download this tool. It's available on this Git repository. So thank you for listening, and I'm open to your questions.
Thank you very much for the talk. Do we have questions in the room? Maybe a first question from my side. Did you implement strategies to measure and optimize the coverage?
So this tool is blind to the software it's testing, which means it doesn't know what it's really doing. So we don't have tools to measure the coverage, the actual coverage. You can only do that through making sure your scenarios, your editing and scenarios have a good coverage.
Okay,
yeah.
Thank you.
Thank you very much for the presentation. My question is, so the idea is to do some fuzzing. So ideally, you would need an example where you're able to crash a program, and you would be able to reproduce the crash consistently based on your parameters. So that's the first question. Do you have an example of such a crash? And the second question is, what is the granularity of the time events that you're doing? Because if your crash is based on a race condition, you need to be able to control the parameters very precisely.
So we didn't do this for debugging software. Instead, we do this for malware analysis. Our goal is to trigger malwares, sometimes viruses that hide into some software. So no, we don't have example of generating crashes.
But did you trigger the malwares consistently?
And we mostly focus on goodware for now, because we wanted to measure the what is a normal behavior for AI models. And about the time precision, I've tested it. I've run multiple tests on different sequences. We are at the system accuracy, which means that, for example, even at very long sequences, we can reach the time precision on the order of a nanosecond.
Okay, thank you.
Thank you. Any other question in the room? Okay, maybe last one for me. But I guess I have already the answer. But do you have strategy to minimize your data set? But as you mentioned, as you don't know what's going on in the program,
to minimize
the data set, the vector that you input on your fuzzer.
What do you mean to minimize?
The number of
the recording, you mean?
Yeah, number of recording, number of data, and number of vectors that you input in your fuzzer.
Minimizing is done mainly by the synthesis of events. On the other hand, you should not try to minimize it to make sure to increase your code coverage. The more recordings you do, the more the better the code coverage.
Yeah, but
on the other hand,
for given coverage, you would like to minimize the data in input. But as you cannot measure the coverage.
On the other hand, it is a trade-off of all the recording you will do and the transformation you will be able to apply. The randomness built-in in the events you will manually add. So it is just a trade-off between all those things.
Okay. Thank you very much. I guess we can thank you again, Vincent, for the presentation.